I actually, just so that you know who I am, I'm Venkatesh. I used to be the Dean of the School of Engineering and Applied Sciences until 3 years ago, and now I'm a professor of technology and public policy in the School of Engineering and at the Kennedy School. And I actually am a strong believer in the interrelationships between especially engineering and society. I feel very strongly that engineering education needed to change. We were too much dependent on science and math and physics, etc., while engineering is its own discipline. So this is not my lecture, but I wanted to say that I have always was fascinated as a youngster with robotics. And you know, things take a while. It's amazing how actually robotics has advanced. And today, we have one of the foremost leaders of this field, and I may not be able to pronounce the name perfectly. If we can say Narayanamurti, then we will say that we are square. Behrokh, Khoshnevis.
Very good.
He is a professor of industrial and systems engineering, mechanical and aerospace engineering, and civil and environmental engineering. That's already 3 departments. So you know he crosses many boundaries, and is the director of the Center for Rapid Automation Fabrication Technologies at USC. I think he is very well recognized as fellow of the Institute of Industrial Engineers. He has a lot of accolades. But what is really fascinating, if you look at robotics, the field which I come from now is nanotechnology. It's the field of the small. And you have a lot of micro robots. And then he is bringing actually, he's also a NASA fellow, National Aeronautics and Space Administration. And my nano people all know about him. So the point is, he has gone, and really because I was walking the school, I wish we should have had him give the lecture in the School of Engineering and Applied. He did talk at the Wies Institute yesterday, and we have, of course, efforts in an area where robotics in the small is really advancing immensely. So it will be very interesting to hear from our speaker here today how it is changing things at the other scale. And I personally am very interested. So thank you very much for coming.
Thank you very much.
And I hope my introduction was okay.
It was wonderful, thank you. Good afternoon, everyone. This is a small group, so it will be good if I get to know also who you are. There are 2 people here who came here through me. The lady there, Dazal, I just recently got to know her. She is a journalist student at New York City University. So she found out that I'm coming here. I don't know how. And she contacted me and came here yesterday and today. She has interest in this house building issue and helping of the deserving population of the world. And this is Dr. Mike Rubenstein, who used to be my former student at USC. He is now a research faculty at engineering school here. His field is robotics.
Yeah.
So, would you please introduce yourself?
My name is Rick Lando. I'm with HILR and IQSS. I'm retired, but I try to keep up on things and spread ideas that I find useful.
What are those acronyms?
Harvard Institute for Learning and Retirement and Institute for Quantitative Social Science.
I see. Thank you. You want to say more about yourself?
Sure. This is all Bennett. Like you said, I go to New York University. I'm getting my master's in news and documentary, and this summer I'll actually be doing a piece basically on this topic and how it basically can turn around the developing world in areas that really need it.
Our design school should be jumping all over this.
Yeah, they are there.
there.
Where are they?
I'm from the Graduate School of Design.
Here.
It also is next door, by the way.
Well, can I just explain? I'm actually an adjunct professor there. My main life is practicing structural engineer in London.
Oh, I see.
So I have a big office. It's actually building quite a lot of stuff and trying to do this kind of thing. I'm now doing research with the architects, although I'm actually a fellow of the Institute of Structural Engineers.
Great. So I know several professors at
I'm sure.
Graduate School of Design, and I have given talks about the topic before over there. And the lady?
Irem Sattar, I'm getting a doctorate at the law school.
Oh.
But I also happen to intern with the South Asia Institute, which has helped organize this. What we're really interested in doing is this Professor Rahul Mehrotra, who is at the School of Design also. He's got this whole Atlas project where he's mapping urbanization in India, and what he wants to do is extend this across South Asia. So he's trying to create a typology of the kinds of ways that cities are developing and expanding in. So we are going to do some summer events in the region, particularly in Pakistan with him this coming summer. And he'll be meeting with several architects and urban planners and students there at academic institutions. So my interest in this is from that urbanization perspective.
Wonderful.
My name is John Harris. I was involved in all three of the Boston area solar decathlon houses, which is the solar decathlon is a U.S. Department of Energy competition, happens every 2 years. Universities from around the country kind of come up with their own ideas for a state-of-the-art solar house, and then they build it. And then it's in a competition, usually in Washington, D.C. And I've been involved in 3 of those houses.
Right. Lou just walked in. She is the wife of my current PhD student there. She heard that I'm coming here.
Yeah.
So you want to introduce yourself?
Okay, I'm a PhD student in applied physics in a school of engineering and applied sciences, and my research work is about thin film deposition. So I think the mainly thought of these two methods is a little similar. So I'm also interested in this direction.
Right.
I'm Michael Bell. I'm a Behrokh Institute Fellow. I work in the Jennifer Lewis Research Group on 3D printing of electronics.
Wonderful.
Yeah, my name is Bob Ahn. I'm working on Jennifer Lewis Group.
Right.
I'm working for printing electronics and solar cell and printing batteries and solar things.
Right. Mark, do you want to say anything more about yourself?
Nothing fun.
All right. And you
I'm
just...
Meena Hewitt. I'm the Associate Director of the South Asian Institute.
Oh, great. Very nice meeting you. And Nora?
I work at the South Asia Institute as well.
And the South Asia actually brings together, to say, okay, there's a core department, FAS, or South Asian Studies, more on the culture and so on, but the others like engineering, what you call design. We have actually a designer from India who's actually a member of the committee, Behrokh, I wish she were here, and because really urban design is a very important element. And then the business school, of course, Tarun, who actually runs it, and also School of Public Health is quite active because health issues are very vastly important. So I would say that's, and the Kennedy School, of course. These are, it really involves all the schools, but these are sort of the dominant members. Is that sort of right? Have I missed anybody?
Yeah.
And no, yes. Hi.
Hi.
Just make yourself, you can come round the table itself, you know.
Okay.
Yes.
So everybody introduce themselves. Would you like to introduce yourself?
Sure, I'm Guy Dietrich. I'm a Harvard ALI Fellow, which is the Advanced Leadership Initiative with the Business School and the Kennedy School of Government.
Wonderful.
And I'm visiting from Palo Alto, California. And I'm very interested in what you do. I saw your TED presentation, and
Thank you.
It's a very diverse group, as you can see.
I
That's
see.
really the point, right?
I see.
Yes.
Very well. So, yeah, the topic is automated construction by contour crafting. That's the name that I gave to this fabrication technology. Initially, it really was not intended for buildings. There are a few commercialized technologies right now in 3D printing. The concept has been around for about 30 years. We should wonder why all of a sudden people thought about layer-wise fabrication of objects. Why so recent, you know? So the issue is that we have made advancement in automation. We like to automate everything because of the advantages of automation. It is fast, it is accurate, it's repeatable, consistent. It removes people from dangerous situations and many other benefits. So constantly we are after automating things. And in the area of fabrication, of course, there have been a lot of advancements since 1950s. We created numerical control machinery, which basically use subtractive methods. They remove the unwanted part of a block of material in order to arrive at the object that we desire. Most precision metal cutting operations right now are based on that. technique. And there are many variations of that on sheet metals and other forms of stock material. Those technologies are applied. The problem, however, is that they are restricted with respect to accessibility. You cannot, for example, make intricate features within an object because a tool cannot necessarily reach it. The other problems are with creation of a lot of waste. A lot of chips are created and wasted. And the other thing is the complexity of automation, because you typically need a large array of tools, and you have to change these tools in the course of fabrication. You have to change the resting face sometimes. Now, if the machine is totally automated with respect to these features, it will be very expensive. So most of the CNC machines require operator interference, for example, to reposition the part in order to cut the side of it. For example, then after every repositioning, there's manual calibration and all that. So it's slow. It takes some human interference. So, for example, to put a CNC machine on the moon and expect it to autonomously work, is a unrealistic kind of expectation. Now, so people have thought about additively building stuff, and so a lot of people thought about automatically building the way that the sculptors build the stuff. So additively and formatively and subtractively. It's a hybrid process that they do. They press things in, they add material, and maybe they remove a little bit. It's a very complex cognitive process, and the dexterity of human hand is involved. People actually have tried to automate that process, and they have failed. It's very complex. So then the idea of building in 2D rather than 3D, approaching the problem of additive fabrications in 2 dimensions, and then stacking these two-dimensional objects in order to arrive at the 3D object seems to be really the only feasible way at this point. So this is why they are doing it. It is much easier to create 2D stuff, and the other wonderful advantage is that the part that you have not yet built is not on your way. Therefore, you have full accessibility to build inside interior features of an object, so things that were never possible before are now possible. Again, because what you have not yet built is not on your way. So as a result, there have been a number of technologies around. I don't want to go through all of them. The first one actually was this one, stereolithography by Chuck Hall, who was an engineer at DuPont, working on the photopolymer material, which has had applications in print industry and in dental industry. For example, you've noticed the composite fillings that they put, and they use UV light and it cures. So the same concept, except that you use a liquid monomer that is exposed to UV light through a UV laser beam that scans the surface and creates the cross-section of the part profile. And the part keeps submerging inside the liquid, and the process continues, and you build basically your 3D object inside the liquid. At the end, you just take it out of the liquid. So the process of UV exposure polymerizes the monomer and solidifies it. This one was invented at MIT later on, called by my friend Ellie Sachs. This is spreading the powder layer by layer. Just any powder can work. For many years they used starch, and they inkjet print glue. For many years they used sugar water. Actually, it's not a very strong glue. It's a two-stage gluing. Initially just loosely holds it together, and then you impregnate it with stronger glue. So you can use sand or whatever. This one uses laser to melt particles of plastic and more recently even metal in order to build the part. So this laser is much more powerful. So I actually independently thought about this in 1983. Around the same time, somebody else at University of Austin thought about it. Probably, most likely earlier than me, he thought about it. But the obsession stayed in me. I really wanted to do something new myself. And I created this technology called selective inhibition sintering, which competes with that approach, but it doesn't use laser. I basically print with a chemical on the periphery of every layer of the part, and then I expose the whole thing to a cheap source of heat, like a nichrome wire or the kind of things that you see on a stove top. By radiation, radiative heat, I just fuse those particles, and the parts that have been affected by the chemical will not be fused. So as you see, like that ball bearing came out of that whole thing assembled using this method. Now we are extending this method to metals. As you see, that part on the left has been made with metallic powder using this technology. So, but I was unhappy with the speed of all of these processes. And I was thinking about a way of increasing the speed. Even today, if you were to build some small object like this, it's going to take an hour or two on these machines, simply because they use very thin layer successively, and every layer needs some kind of processing. You have to do material delivery and then some kind of processing in order to fabricate that layer and continue on. So I thought a lot, and I concluded that there's really no way other than increasing the layer thickness in order to increase the speed. But if you increase the layer thickness, you lose surface definition. And you get, for example, for slant surfaces, you get this staircasing effect, right? So the concept came to me when I was filling a crack after the earthquake, Northridge earthquake in Los Angeles. We got big cracks on the living room and other places. So I went out and bought some plaster and putty knife, and as I was filling that,
I was in Santa Barbara at that time.
Yes. So as I was filling these cracks, it occurred to me that the simple tool has great capability in producing wonderful surfaces. So then it occurred to me that if I automatically feed this trowel with material, paste material, and move it in 3D space using a robot, then I should be able to use very thick layers and create very smooth surfaces.
Well, that's what the artisans do, don't they, actually?
Right, basically, right. Exactly, right. So these are some of the early trials, as you see. That thing, the layer there is 6 millimeters. Compare that to typical 3D printing that has got a layer thickness of under 1 millimeter. Usually it's 0.25 to 0.1 millimeter. And the surface quality here is better than even those that have got sub-millimeter layer height.
What is nozzle diameter?
In this case, size of every one of those, the size of this has got a square orifice. It's about 8 millimeter. Right. So these are some of the ceramic objects that I produced. Then even sharp corners are possible, as you see, with certain algorithms that we use. The overhangs are possible, and so on. So imagine that this could now be thought about as a roof of a house, for instance, or that. So when I looked at these objects, it occurred to me that the potential for this technology really does exist for building very large objects, because the speed was acceptable now. So then I moved into creating hybrid objects. For example, this is plaster here, and inside of it is cementitious material, harder material, structural material, and this is soft plaster material. So you get beautiful outside, but the structural inside. So then I embarked upon building concrete structures. And well, when I went to our civil engineering professors, they really discouraged me by saying that, hey, you don't know concrete. You cannot make concrete stand on its own like that. Concrete is made to flow and have a lot of slump because it has to be molded. So the mindset was the status quo, right? I had the advantage of being naive, you know. I just didn't believe them, right? Because I was not used to that status quo. So I said, well, we'll try concrete. If it doesn't work, you know, the idea is good enough for somebody to develop the right material for it. But we kept at it, and eventually we managed to extrude concrete, the kind that can stand on its own, hold its shape. So the challenges were several. One is, of course, the low slump and keeping the shape, but the other one is just extrusion of highly abrasive fluid. You know, just try to put this much concrete inside a tube that is this long, 1 inch, 1.5 inch, whatever in diameter, and try to push it in with your thumb. You'll notice that it gets stuck, it won't go forward, because this granular particles create a bridge. They press against the walls of the conduit. The more you press, the harder it gets for them to move forward. So this was the big challenge. And what happens when that occurs is that all the juices go through under the pressure of the pump. All the sand and gravel stays behind, and you get like a rock hard clogging. You have to use hammer and chisel to actually get it out. So we struggled with that kind of problem for a year and a half and so on. And the result that you see here is after we overcame those problems. So it's a two-stage thing there that fills the thing. And then we advanced to the housing applications. Well, you've heard about Maslow's pyramid of human need, at the base of which are the two essentials, food and shelter. Unfortunately, at the dawn of 21st century, this is the condition of shelter for more than 1 billion people. Some statistics say 2 billion people in the world are living in such slums. I have visited several places in the world, like shanty towns in southern South Africa, other places in Mexico, and so on. And some conditions are even worse than that, believe it or not. So governments, of course, are aware of this problem. They would like to have decent housing for their citizens. However, they're facing the problem of conventional construction, which is slow and labor-intensive. It is most hazardous job in the United States. It kills, 6,000 to 10,000 people every year. About 400,000 people get injured. A lot of those injuries are very serious, like spinal cord injuries and so on. And of course, in the end, the customer pays for that. The insurance that construction companies have to buy, all the litigations that are involved, result in the higher price per square footage that people pay. And that's why one reason automation is cheaper, because it doesn't have those problems associated with it. It is wasteful and emission causing. You've noticed everywhere there is construction, there is typically a huge dumpster, right? All the trimmings and material that has been set, things that have been wrongly caught and all that, they dump them there. And also it's interesting to note that 40% of all materials worldwide are used in construction. So if you have waste there at this significant rate, you can imagine the impact on the environment. It is really huge. It is corruption prone. There are many different trades involved in there. The management is difficult, and it's costly and always over budget. So the solution that we propose is something that will create dignified, nice neighborhoods instead of those slums at affordable cost, at a fraction of time, and far more safely, and with ultimate architectural appeal. So they will not look cookie cutter like this. I just grabbed that from internet. Because the process is computer driven, there is no learning curve involved. So you don't have to repeat the same designs. You can have every design different than the other. Well, this animation, which is a little jumpy now, shows the basic concept. So you can set those rails in the street, for example, or where there is a development, and you can have this machine build one house after the other. You bring the architectural design on a flash drive and put it in the controller of the machine, and bring the material, and you press a button, and the thing will be printed. The building will be printed for you. So again, much like any other 3D printing, it does not need that much of an attendance. The machine is pretty light, and few people can carry it to the site. You know, it collapses on a flatbed truck. You take it to the site, and in a matter of 30 minutes, you erect it, and everything is laser guided. You know, it's self-correcting. The rails even don't have to be very well aligned when you put them down, and there are many operations that can be automated, even building the foundation.
So the site itself is the manufacturing line, so to speak.
Exactly. So we
And,
take it.
and, there,
right.
and you have put some, can the rails disappear afterwards?
Yeah, you lift them afterwards. You
You
take
lift them afterwards.
Right. Right.
What's the consistency of the concrete? What is it?
What do you mean by
10,000
consistency?
You said with low slump concrete, so I have two questions. One is what's the thickness is typically?
10,000 PSI.
And the other is what's it made of? Concrete. It's sand, cement, water. The same thing. But
Yeah.
very low
So,
slump.
right. The cement is well.
Normal
You can
concrete.
use Home Depot concrete. The first wall segment I showed you was Home Depot concrete,
Right.
but we added the right admixtures to it
To make
that
it
we
what?
learned to make it low slump, to make the rheology good, so they can be pumped and flow through without that segregation kind of thing.
So is it more, why I ask, is the common one is self-compacting concrete, which is very liquid.
Now, we don't want it to be self-compacting because then that's high slump, right? So we have a process where we build the edges, the rims, this outside with zero slump, the middle with high slump. So we bring the same concrete to the nozzle. At the nozzle, we separate it into two channels. To one of them, we add the chemical that adds to the slump. The other one, basically a chemical that reduces the slump and accelerates the curing.
So what's the thickness of the wall?
Well, it's variable. This one that, well, let me show you. Okay, so a model like this, a house like this is very easy to build with this technology. And of course, whenever you curve the buildings, you gain strength. Even with the same poor material, like Adobe even, you can make stronger buildings. I'll show you an example later on.
How do you get over the strength of the concrete, like coming from USC or used to earthquakes? It doesn't seem like it'll be very reinforced without rebar or something. Is that
No, we can put rebar in there.
like full length bars? Or
Yeah, you will see the next animation. So, building with curves is difficult to do, especially if it's doubly curved and so on. It's very expensive, but for technologies that are computer-driven, it really makes no difference. So this is the answer to your questions. This is automated reinforcement. We have many different approaches. This one uses segments of rebar that are assembled onto one another. This is building a two-dimensional mesh of steel automatically. The device that you see there is an accessory that is mounted on the same gantry robot. So it's a very streamlined automation. For every so many layers, you have the segments of, for example, copper pipes that have got solder in the inner rim, and electrically they're heated and fused. So you build the whole plumbing network in the building as you build And also you can do the same for electrical network installation. These polymeric blocks can have power lines and communication lines in them. All you have to do is, again, for every so many layers, you plug them in. And it's just like Lego blocks. We have different designs of those for T-junctions, for corners and all that. So this shows you the video of the operation at the smaller scale. Some of those ceramic parts that you saw, this is the machine that builds it. This is a 2.5D structure. Again, imagine if you were to build this thing with conventional method, you have to have a formwork with lumber to be shaped like that, which is very difficult, if not impossible. That one is true 3D. The trowel is constantly changing its angle as it's moving around.
What did you mean by 2.5D?
2.5D is that the cross sections are the same as you go along the z-axis. True 3D cross sections keep changing.
What is
So-
the printing speed?
That's the printing speed that you see
Yeah.
there. You can get, so that is about 1 inch high every layer, and we can go at the speed of 1 foot per second. So 1 square foot of the wall can be built in 12 seconds. So you can now imagine how fast the whole building can be built. Like a 2,500 square foot building can be built in less than 20 hours. On-site, custom design. And we have many different ways. You know, this thing
So
has...
it will only work how with materials which will flow like this, like concrete and
Right.
so on, at the moment. Until
Right, but you know, we have tried many different materials like gypsum and plasters and stucco material, and we have actually tried with composite material that are made with wood. Like if you take sawdust and wood chips and mix it with epoxy
Yeah.
and extrude it, you know, it will work. You know, anything
will
you can turn into paste,
Yeah, right.
it will work.
Which you can extrude or mold.
Right. So look at this S-curve thing. If you were to build this by hand, you know, it's really difficult. You know, how would you do it? How do you form the lumber like that? Well, you've seen this. So this is one of the machines that we built. This machine is about 500 pounds. It's very light in weight. It makes almost no noise, and it's very agile, relatively accurate. You know, so it gives you like millimeter accuracy. Typically in current construction, it can be few inches off and nobody notices. This thing is really accurate. So, and of course it uses wet concrete, no dust. You can get up in the morning and see a new house built next to your house, you know, without you having noticed it. Because it makes no noise, it doesn't make any dust. This is one of the more sophisticated nozzles that builds the outside and inside concurrently, so that is super fast. Some of the challenges here have been regulating the flow of concrete. Concrete, aside from being a non-Newtonian material with all kinds of aggregates and abrasive stuff in it, it also has got air bubbles in it. Therefore, it's like sponge, you know. It's what you press on one end does not necessarily come out on the other end. It's like pressing a spring into the hose. So what you do is that you keep on pumping and pumping, and all of a sudden, a lot of material jumps out from the other side. And then it gets stuck, and then it jumps out again. So how do you regulate the flow to see, as you saw, it was coming out very smoothly, the flow rate is relatively accurate, and that's why we can consistently build those structures. So how do you do that? That has been some of the main challenges that have taken a lot of my time. Anything that deals with concrete has to involve metal and rubber. You cannot have metal and metal. So rubber, of course, wears out. If it wears out, you lose the juices. If you lose the juices, you're going to
Can you use materials like, unlike concrete, which obviously is a big building material, but of course, in fancy homes you even have what you call Teflon and those kind of things. And presumably the plastics industry, and those, they have learned the molding and extrusion properties.
Right, right.
Is it possible to, yeah, obviously that
For certain features, we are actually considering that. That gets back to conventional 3D printing that they use plastics. So for like kitchen appliances and stuff, like for kitchen counters, we have looked at using polyester materials that are used in combination with concrete. Yeah, all of those are possible. So the vision that I have is total automation of building construction. Look at these cars that are being made almost automatically today. They're much more complex than buildings. They're made with more difficult materials. The accuracy, the precision is much higher. The geometries are far more complex, and yet they've managed to do those automatically. These buildings.
You still have human beings, but a very small number. Highly intelligent.
Exactly. But these buildings are relatively simple. The only problem with them is that they're too large and they're not mobile. We cannot take them into the factory. We have to bring the production equipment to the site, and they're subject to the elements sometimes. There's wind and dust and rain and so on. So these have been the barriers against automation so far. But look at the 3D printing concept. I said since 30 years ago, we started thinking about building layer by layer, the objects, small industrial objects, and consumer products like this. But for thousands of years, we've been doing this in construction. We've been building buildings layer by layer using bricklaying, right? So it makes perfect sense to bring these two together. In fact, this technology of 3D printing is for construction, in my opinion. Its major impact will be for that. And construction is the biggest sector of almost every economy. It is the biggest sector in the US economy, over $1 trillion a year. Of course, some of that is road building and tunnels and all that don't apply here. But a good portion of it is building industry and infrastructures like bridges and so on that this thing can handle.
Can I ask one more question?
Yeah.
How do you compact the concrete? Because you said it's not self-compacting, and it's just poured, but do you not need to compact it? Is it a different type of
it is, I don't know what you mean by compaction.
Well, to get strength in an ordinary concrete, you need to compact it. You either use a vibrator or you use
aerated.
Okay.
Right. So, no, this is under pressure. You know, the pressure here is about 200 psi when it comes out, and it is pressed onto the previous layer, which is already firm by the time you put the new layer on. So that is very well compacted.
So the strength is gained.
Yes, right. You don't have big bubbles of air in this thing.
Right.
Yeah. And again, in the middle of those, if you want to fill them, you pour self-compacting concrete.
Yeah.
Okay, and we have methods of doing that. We have nozzles that develop this, as I told you, that they can extrude on the side a different kind of concrete than the one that goes in the middle.
You've got 90% of the answers here, I'd say. But what I'm interested in is what are the bits that are patented? Is it the nozzles and the chemical, or I've never seen one that's as successful as this, I have to say, and I've seen quite a few.
Yeah, well, I'm the one who started all this thing.
Yeah.
And people in Loughborough and others, I've had connection with them. I got them started on that. You know, some of them were my associates. But nobody has thought about this as much as me. I'm not smarter or more creative. I've just spent a lot of time on this. There have been many nights or mornings I walked out of the lab at 3 o'clock, 4 o'clock in the morning. Mike knows that. Wet, with concrete, We start at 9 o'clock in the morning. I got out of the lab at 4 o'clock next morning because it's a tough project. In preparation, we need several people mixing the concrete, preparing the machine, the program and all that. And after we are done, there's a lot of 5 hours of cleaning. You have to take everything apart and clean them. It's a very stubborn material. And of course, our parts are not necessarily made for frequent uses. Everything is prototype, so they're not quick release. So look at that beam. That is a section of the wall 10 hours after fabrication, and look at the strength of it. That's a 10,000 psi concrete. It's got composite fiber in it, very short 2 mm fibers, a few microns in diameter. So you can use this as beams. You don't have to have wooden beams or anything for the roof. For the doors and windows, you can use them, the lintels. This is automatic embedding of yet another form of reinforcement. This is putting coils in there automatically. This could be steel coils for reinforcement, or they could be like nichrome coils for heating. Or they could be tubes for cooling or whatever, and you can pass cold water through it. There's a lot of things that you can do when you build things layer by layer automatically. You can insert sensors. The brown material you see there is conductive concrete. If you add carbon fiber or even graphite to concrete, you can make it conductive. So you can insert these wireless sensors that are powered by the wall, and they can report on, structural health monitoring, like parts of bridges and things, buildings, intruders, temperature, whatever. These days there is translucent concrete. Concrete is basically rocks and cement. Cement is anything that can glue the rocks together, right? So if instead of the rocks you use pieces of glass, and if you use some translucent glue, there are a lot of glues are translucent, right? Then you make some form of concrete, right? And the German company has done the same.
With reasonable strength.
Yes, with reasonable strength, of course. That is structurally approved strength. So you've noticed some of the bathrooms, they use this glass tiles that they put there. It's equivalent of that kind of. But this area is improving fairly rapidly. Now they're using some segments of optical fibers into the thing. So better conduction of light, saving energy, parts of the building. Robotically, we have different kinds of applications. Like this is a gantry system like the one that you saw. For larger buildings, for increased speed, you can have a multi-nozzle system like that. So this will be many times faster. Therefore, a huge building like an apartment complex, school, hospital, government building can be built in reasonable time. You can build high-rises when the machine platform can actually climb the building as it builds it. The whole platform is light. And for example, if you put segments of tubes every so many layers in the wall, you will have these pretty good bases to insert those pins in and kind of walk the machine up. And after it is done, it can come down. In the usage life of the machine, another frame can be used to automatically clean and paint the building or clean the windows or whatever. Once you prepare if you build the building with automation, you can conform it to other forms of automation. Maintenance, again, is one of them. So yeah, this is the building that I referred to. Look at this gorgeous design, which is made with only adobe material, clay and straw. It's over 200 years old. It is the house of a carpet merchant in the city of Kashan in Iran. You can go to the internet and see other views of it. It's just amazing architecture. And of course, Iran gets a lot of earthquakes, and this thing has experienced a lot of those earthquakes, and yet it's standing up erect. You can test with a piece of paper. If somebody gives me one page of paper, Lou, do you have a loose? Yeah, just pass it. Well, the worst kinds of walls are the ones that are made in a rectilinear way, straight planar walls. You see, this paper cannot hold its own weight when you hold it straight. But if you curve it a tiny bit, it gains a lot of strength. So with the same weak material, you can make much stronger structure if you curve things a tiny bit. But when you build things manually, it is hard to curve them. You know, how do you follow like a polynomial with simple construction workers? I mean, it's not really possible. But again, when you do it by computer, you can do wonderful stuff.
So that building is 200 years old.
Yes.
Reinforced concrete, and it's just the
It's
curves of
clay.
concrete.
It's only clay, no
It's
concrete.
Adobe material, you know, the way they,
Adobe,
yeah.
okay.
Yeah,
But
it's
unreinforced.
no, it's reinforced with straw, pieces of straw. So they're like this big, this long, piece of straw, and wheat straw is amazing. You know, it's got very strong fibers in it, and it lasts for centuries.
Does Adobe have self-healing properties? So if a crack
Yeah,
forms,
right. And of course, yeah, very good point, Mike. Probably in every earthquake, this thing gets thousands of cracks. But every time it rains, you know, it self-repairs itself. You see? So that's another wonderful thing. Now they're looking at, like the Air Force in the United States is looking at use of geopolymers and clay. So with the local soil, they add about less than 5% geopolymer, and they get concrete-like structure. So this way, they just carry a little bit of geopolymer to a site on an airplane or whatever, and then there's soil everywhere, right? So we can use the same kind of material with this technology, and again, we can add to the strength and beauty of it using these nice architectural features. See, I don't know about you, but to me, these kinds of spaces are much more organic, much more friendly to human psyche, I think. I like it better. See, this building is very simple. It's made with vaults, you know, half cylinders and domes, basically. And this is how they build them. You know, these are ingenious patterns that they follow. Without scaffolding, without any support, they make these structures. For centuries they've been doing this. Well, it may be hard now to find those people to do those, therefore it will be expensive to do them by hand, but robotically we can follow the same patterns. You know, we can program the robots to do the same thing. In a supportless way, we can build totally enclosed structures. So therefore, using in situ material, we can build wonderful structures like that. I wrote a paper a few years back, and I mentioned that this could be used for remote areas, including other planets. If we put this machine there, and if we get the local material, at the time I didn't know exactly how to use the local material, but I kept thinking about it. And I came up with an idea, and that's why I have the current NASA projects. So this was one of my attempts in collaboration with NASA Marshall Space Flight Center. This is a design of a lunar fuel vessel. One of the applications of Moon is using it as a launching platform because the gravity is much lower there. And you can get rocket fuel there from the local material, and you store it there, and future launches can be done from the Moon. That's one of the applications of Moon. So our NASA project, the new one, is NASA Innovative Advanced Concepts Project. It's a program that once in a while NASA announces. This time there were 800 proposals submitted. They funded 30 of them, and one was mine, to my surprise. So basically what I did was that I kept thinking about how to use the in situ material there. You know, water is hard to get. There's a lot of ice on the polar regions of the Moon. Although there's vacuum, the temperature is so cold, so low that you don't get much sublimation. So there is ice there. But even if you can melt it and make concrete, in the presence of vacuum, it's not going to last long, right? It's going to immediately dry up. So you have to do it under a pressurized vessel. So that's out of the consideration. So I thought about, I was in Hawaii, you know, I don't know if you've been to the big island and you have seen the flow of the lava. So I made the connection that, hey, if rock can be molten like that on Earth, we should be able to melt the rock on the moon as well. So that was the principle of the idea. So I got some lunar regolith simulant from NASA. I bought some. And I bought a Fresnel lens from Edmund Scientific, and I went to my balcony and I tried to melt it. That was the only way I could create high temperatures, you know, didn't have the furnace at the time. And I melted the thing, and I created a systematic experiment. And I managed to do a concrete-like structure, you know, certain elements melted and certain others didn't. So those that melted worked like cement, the others that didn't melt worked like aggregate. So I created the cross-section, look at that, and I put them under standard ASTM test, you know, for compressive, tensile, flexural, and so on strength. And by now I was much more intelligent about what is out there and what can be made with it. And on the basis of that, I wrote this proposal. So although I didn't have any space experience and I didn't come from a related department, I managed to get this proposal funded. And it's been one of the greatest things that happened to me because I've met wonderful scientists at NASA, and now the project has advanced. So we are supposed to build precursory infrastructures. My talk yesterday was about the details of this project, so I cannot spend too much time here. But you know, the equivalent, the analogy right now of going to other planets is like when we first went to the Arctic regions or Antarctic region. A single-engine airplane that was equipped to land on snow was used just for surveying and exploration. Nothing serious could be done back then. And whatever we've done on Moon and we're doing on Mars is equivalent of that. Now later on, of course, we found oil there and all that. Now we have airports there, we have establishments there, infrastructure there. In order to do anything serious on these planets, we have to have infrastructure. We need a landing pad, first of all. The future landers are not going to be light anymore. We cannot land on sand. The last lander that landed on the Moon almost tipped over. Another 6 degrees and it would have tipped over because it landed on soft sand. The exhaust plume pushes the sand away, and under that it was a sloped rock. It wasn't horizontal. So that's one thing we need. Then if you have a settlement there, you need a blast protection wall. The projectiles are thrown at 4 times the speed of bullet, and if they hit an astronaut or equipment, they're definitely going to destroy it. So you need to build a blast wall there. You need to build roads to connect the landing pad to the settlement. We need those hangars to store the landers and other equipment to protect them from micrometeorites and all kinds of radiation, solar and cosmic radiation. So the way we are doing this is that we are melting the regolith in a contour crafting attachment, which is put on top of a NASA rover. That rover is built at JPL. It's a 6-legged rover. It's called Athlete. So we're melting the regolith using microwave and extruding it and building layer by layer. Another thing that applies to the Martian especially situation where SpaceX is interested in it, and we're hopefully soon starting a new project with the SpaceX, is the application of sulfur-based concrete. So I remember from childhood that they were connecting ceramic insulators of electric lines to the metal piece that would screw onto the beam using sulfur, molten sulfur. So I remember that, and I noticed among the constituents on Mars, especially sulfur. So we can get sulfur, which melts at pretty low temperature, 130 C, and mix it with the local Martian material and send it through a heated nozzle. This will not work everywhere on the moon because it can get pretty hot, hotter than that under direct sunlight, and the structures would melt. But on Mars, you know, the highest temperature typically is about 0 centigrade. It's ideal for sulfur-based concrete structures. So back to the construction on Earth, the cost of construction, about 20 to 25% is due to financing. Well, we build almost instantaneously, so that's the time value of money for the duration of construction, the money that is tied up in construction. You get your building almost instantaneously, so you pretty much save all of that. The material will be more expensive in our case because there is R&D going on to it. Gradually, that is going to lower to the current conventional cost. But we have zero waste, so I assume in the long run our cost for material will be less, and we almost eliminate the labor. So as far as the competitive landscape is concerned, with respect to construction cost, contour crafting is lower than even prefab manufactured, like mobile homes and so on, prefab modular, and definitely far lower than conventional construction, maybe only higher than emergency construction, like tents and boxes, connexes, and so on. With respect to architectural flexibility, with respect to speed, of course, nothing really beats contour crafting. We even compared building the collective emergency shelters that the Army builds. It takes 4 people and half a day. We build totally autonomously in about an hour, you know. So we build a concrete shelter compared to a tent is faster, and it protects you against explosives, chemicals, radiation, and so on. Much better than tents. So with respect to environmental impact, the CO2 emission of conventional construction is shown against the green one, which is emission related to contour crafting. Now, most of the excess emission in the conventional construction is due to people driving back and forth to the job site every day for the long period, the duration of construction. And embodied energy, of course, is much, much less than the current one. Again, most of the energy there is spent in gas fuel, right? People going back and forth. The machine is fully electric. You can have your little generator if you want to build in the middle of nowhere. You can even use probably solar panels, right? Build in the middle of desert. If we combine the NASA findings, we can actually build without water in the middle of desert using sand, you know. We are now, actually the state of Hawaii has expressed interest because they're producing a lot of sulfur, and their whole island is made with volcanic rock, and they have a lot of sand that actually looks like lunar sand, and the lunar sulfur concrete is really, really strong. So we think that...
But sulfur is slightly hazardous, isn't it?
Well,
it can catch fire and SO2 and, you know. Right?
There are ways of making building retardant by putting layers on it. Yeah, all of those are
Or
issues.
do that research, right?
Yeah, but it's not necessarily for housing, you know. You can do it for other infrastructures. You see? So the impacts of these technologies will be many. Hopefully contour crafting will be a technology that will start the whole thing. We are making an attempt to bring it to the commercial realm. But there will be always, of course, other competing methods. So the impacts will be on economy, employment, social, regulatory, environment and architecture. So the employment impact is a sensitive one. A lot of people ask me, what's going to happen to these construction workers? I always give them the example of the typists who were around at the time I was writing my thesis. We used to write them on a piece of paper, a stack of paper, and give them to these poor people to type. Almost all of them develop carpal syndrome, which is a terrible disease. Go to the internet and look at the way of treating this. The surgery is really amazing, devastating. They all developed psychological problems, because of repetitive, non-creative tasks. They never paid attention on, what they're typing and so on. And it was a very bad job. If they made a mistake, they left a couple of lines out. Anything after that had to be retyped. It's not like cut and paste that you see in the word processor today. So that kind of job had to go. We couldn't have prevented the advent of word processing and computers in order to save those jobs. They didn't make sense. And I don't say it in front of construction people, but really a good portion of construction jobs should not be there. I respect the talents that these people have and the courage that they have. They go on top of these tall buildings and they do dangerous things that are also difficult, and they do need some intelligence. But anything that machines can do is really inferior for humans. We should let machines do them, not humans, and let people do more creative stuff.
Well, the question about that, just for comparison, what do you envision as say a work crew, a complete work crew, to build the exterior walls, let's say, of a single-family home?
Well, maximum of 4 people for one day. Okay?
What would each of the 4 people do, let's say?
Well, they will be primarily for setup and taking the machine off and loading it on the truck. Mostly supervision to make sure that the flow of concrete from the mixing part to pumping part to fabrication part is going well. The machine will have all kinds of self-diagnosis thing. At times, if anything goes wrong, it beeps and calls for attention. So that's a big part of this. Right now, if your printer runs out of ink in the middle of printing a page, you notice that the thing gradually fades out. There is no way of repairing that page, is there? If you put a new cartridge and try to print over it, you can never fix that. Well, we cannot afford to have that kind of error. Half of the house is built and then we get a clogging or something. We cannot throw the half of the house away and start over. So there has to be remedial methods that we have actually thought a lot about those. And those involve people. They have to be there in case to fix those. It's much like textile. You've seen these people walking around these textile machines. Once in a while, one of them, snaps, the thread breaks, so they go there and do something manually. That's pretty much it, But, this is going to create, of course, new opportunities, in the design and also like creation of those segments of pipes, the new industries for electrical and so on. There will be new businesses. For the first time, elderly people, female workers will have a chance to work in construction because it's no longer going to be muscle-based. I refer also to this very relevant example that at the beginning of the 20th century, early 1900s, 62% of Americans were farmers. Today, less than 1.5% of them are farmers. What happened, The world is still continuing, we didn't have a major catastrophe as a result of that. The same will be true about construction. Now, those days of farming economy, we didn't have .com companies to hire so many people. We didn't have software, we didn't have computers. We didn't have space technology. We didn't have this vast biomedical kind of industries. And future will be as different as this has been compared to 100 years ago. So we should not worry too much about the change. We should just think about how to bring it about and look forward to the good things that come out of this. Every construction worker anyway lives in a house. They're going to live in a better house and a cheaper house, a more affordable house, right? We're going to have less injuries and fatalities, less load on the healthcare systems and so on. And one thing that is very interesting to me is that wherever there is slum housing, there is density of population as well. I believe by bringing up the standard of living in those regions, we're going to reduce the population of the world by making better life for people. So they won't live in that desperate situation. They would elevate themselves in higher stages of Maslow's pyramid. And we'll have more of inventors in those communities, literally people, and people who will think about their future, have a security. They don't have to rely on keeping creating babies. So we created this Center for Rapid Automated Fabrication Technology, craft. So with the focus on these different areas. So there's technology thrust, of course, that, on materials, on robotics, and on software issues. I believe software becomes bigger and bigger when these technologies happen. The architectural side of this, the logistics side of that, and all will become bigger and bigger in the future. It's much like the printer industry. When they invented those little dot matrix printers, these wonderful fonts were not around. Like Steve Jobs was one of the guys who went after creating these fonts and so on. Desktop publishing was not around, right? So these printers made a lot of things possible. When movie camera came, the art of cinema was not around, right? So the content becomes more and more important as such technologies happen. So I believe in the future, the house design, the building design will go to another plateau. And more people will directly interact with intelligent software that helps them design. And who knows, maybe someday you go to Home Depot, rent one of these contour crafting machines and go to the lot and build your own home based on your own design.
How are the thermal and acoustic qualities of this process? How does that compare to Rastra?
So what is that?
Are you familiar with the Rastra construction method, which is basically prefabricated concrete blocks?
Now, I have not compared them, but basically today the way they do insulation is that they put panels mostly on cinder block or in these prefabs. They either put it in the factory for the prefab or on site. They just stick these things. We can do it on this, but we are working on automated delivery of insulation material as we are delivering concrete. At the same time, we deliver plaster. At the same time, we want to paint it with inkjet printer, wallpaper design on it. So you build a whole complete complex wall with the plumbing, electrical in it, finished work and paint it. So I think all of these are possible. Look what we've done in robotics in manufacturing. The second arm of this watch is automatically placed on that tiny shaft. So the accuracy that we need for this is far less.
And are you actually doing any construction experiments anywhere in the country?
We are building segments of stuff because of the logistics. Hopefully soon we'll have full buildings. People keep asking, what about the full building? The problems with that is that I'm building in the lab, right? If I build a building under the machine, I cannot build anything else, right? So I have to demolish this thing and remove it. That gets pretty expensive. The other problem, if I build outside, my new machines will be able to build outside actually, but that also is problematic.
I've got some land in New Mexico where you could build as much as you want.
Okay.
It's a land of enchantment as well.
Yeah, I have received a lot of offers like that, but I have been also told by some authorities that if you do such a thing, you better put a guard there to make sure some homeless people will not go and live in it. If they go in there and at the same time there is an earthquake or whatever, we will be liable for that. So unless you get building permit, for your technology, they give you the conformance approval to the standards, you're not really allowed to build anything anywhere and leave it like that.
Sure.
It's a very important question.
Well, yeah, I mean, this is great theoretically, but you got to get it out of the lab into the marketplace.
Yeah, so
are you talking to major building companies?
Right, we're doing that. We're doing a lot of that.
Because I think many of the countries, like I know India, for example,
Right.
has a Central Building Research Institute. They should be, in fact, well, obviously you need the land.
Yeah.
University, it's hard to do it in Los Angeles, obviously.
Right.
And they should be interested in actually building some of these and actually implementing this, especially in the developing world. And even in the US. And New Mexico and Arizona would be good places where there are land, where in fact there should be. And so the building industry, somehow, it looks like you're close to a point where actually the scaling becomes really important, that we actually build a real thing.
Yes, and again, our plan is to move forward and do that. Everything needs funding, of course, and our effort right now is on securing the funds. And there's expression of interest from many countries, including India.
Africa, I mean, I've gone quite a few times to Africa.
Yeah.
You really, because but the scaling is somehow you have to be connected with a big building research organization, and building development organization. Right.
True.
Right. They surely must exist, but they're so backward sometimes, these industries, and they don't know how to couple to a forward-thinking person.
Right.
Tarun may have solutions. He comes from the business school.
I have a question.
Excuse me, I need to go. Thank you very much.
Is it a good time for discussion?
Yes.
Yeah, we've already been having this, but I think so. Tarun.
About the recovery from problems, as you said, when the printer runs out of ink, we can't repair.
Oh, yeah.
Is there any way have you simulated common problems in this? I mean, what are some of the things that go wrong when you try this? Or have you not done it at such large enough scale that you would really know statistically what some of the issues might be?
No, we have not done anything too extensively. We've tried to just push this forward and try to demonstrate as many possibilities. What good things can happen. We have not tried to focus on the bad things that can happen, right? Other than clogging, because we had to resolve that in order to be able to make other demonstrations. So we have solved a lot of problems, but we will learn a few new things when we build a full-scale structure. For example, shrinkage effect.
What is the shrinkage rate?
Well,
After
concrete is a wonderful material. You can make it shrink, you can make it expand, and if you engineer it right, you can make it not change at all. Also, it has to do with the ways of delivering it. So we are going to focus more on that. We have a project from a major industry. It's not related to housing, but I'm not at the liberty to talk about it, but for that, we are taking a close look at that situation. We have all kinds of models that we are using. And it looks very good. I mean, it shouldn't be a problem.
I mean, the early application could very well be building sections
Right.
by this man.
Right.
And that may very well be, and then you can do real tests also, etc.
Exactly.
That might be.
So that's what we have been doing
Yes,
right now.
in a sense, that's what you've
That's
been
what
doing,
right.
but now you want to do it with the industry and so on.
Exactly, right. Right.
That seems like the natural way of doing it.
Right.
Because, then you will also learn the issues with scaling, the effects of the reliability and so on.
How about pick and place of bricks and then building that up with concrete?
Okay, so some Swiss company, some Swiss group is doing that. Actually, I'm surprised that this has not yet been done. And the Swiss company is mostly under decorative walls. They are not after building anything serious. So the reality is that when you use, and they're not putting mortars in there, they're just laying bricks, on top of each other. And they keep changing angles. They create beautiful stuff. Look at them in the internet. They create beautiful stuff. So it's not just a simple brick wall. The bricks keep changing direction, so the corners show a pattern, and so on. Now, I assume the reason nobody has done it is because it again involves delivery of mortar, right? Which is like countercrafting. You have to solve these problems. On top of that, you're superimposing pick and place of bricks. And if you've ever seen brickwork, after placing every brick, they typically do a lot of fine adjustment. So I'm not sure if it is a straightforward process to automate at this point, if you're putting it on the soft mortar.
I have two questions.
Yes, go ahead.
One is regarding the recyclability of the material, because you're basically like bonding all of this together, so then you end up with a structure that you can't really adapt anymore. And the other question is regarding to like how you would imagine the design of these structures, because you were mentioning that basically everyone, the discussion is going on with 3D printing right now, that basically everyone can just sit in front of their PC and create these things. But I come from an architectural background, so obviously like from our profession's perspective, we think that we're the people who are trained to deal with space and
of course
design, and that it's not, like in general people always have this opinion that anyone can design a house, and many people do, and I think it's possible. It's just like with these new technologies it becomes a whole new game, I guess.
True. So the first part of your comment was about sections being your assumption is that the whole thing is monolithic, the whole thing is connected. It doesn't have to be like that. We can cut in sections, as we build, we can cut the soft concrete. We have actually done it. So at certain points, you can separate the building if you want. Your other point has to do with people doing design instead of architects, right? I think they're doing them right now. A lot of people do it right now. There are all kinds of software already around. But with tools like this, when these tools become common, you'll design for a fabrication technology. So your software will be smarter with respect to the fabrication stage, the construction stage. So it can give you feedback. Hey, this is not good. This cannot be made, or this will be too weak if you do it this way, or whatever. Without knowing who is going to build it and what constraints it has, it is hard to provide these feedbacks. So I think this will, we're working, we've talked a lot with companies like Autodesk, the Rivet people. So they are interested, possibly getting involved in creating architectural software that are dedicated to this technology.
Are you working with architects as well? Or just because it provides all these
Oh yeah, actually I work with a lot of architects. On my NASA team I have 3 architects. You probably know them. Some of them are pretty famous, I think. Yeah, architects are pretty strong advocates of this technology. I've learned a lot from them. I've been, all over the world with them, to meet them.
Right now, in very recent times, there's been like 2 or 3 projects where, like, there's sort of this race right now, like who's going to print the first 3D printed house. Are these actually serious attempts? Or?
It could be. I don't want to rush into it. I want to do it right. So, depends on what you mean by a house. To me, printing a house is a house that is approved for living. Not just. Right now, I can print something with the machine that I have. You saw that machine is big. If I can print 2 walls, I can print another 2 walls. It becomes a room. If I can print a room, I can print 3 rooms. It becomes a house, right? But I don't do that for this and the other reasons that I talked about.
Yes.
I kind of asked you this a little bit yesterday, with who you think might pretty much invest or pick it up, whether it be like the private sector or the government. But it seems like even if a private company picks it up, you'd have to go through the government anyways to get those permits.
Exactly.
So.
And that's why the private industry is always sluggish and hesitant about construction technologies. It's like going to a pharmacy and saying, I have a better pill for blood pressure. Take this and sell it. Well, they know what is involved in getting FDA approval, right? And they know the consequence of selling a non-approved drug, so they're not going to do it. They're very hesitant. Right? Same thing is true about construction companies. They know that the process of getting approval is a lengthy one, right? And takes a lot of tests, and it's very costly.
Have you looked into any, countries that don't have a very lengthy process in doing that?
Right, we've looked at several of them.
Like,
We are going to most likely work with one of those, to start with one of those.
and then especially with like emergency, like people would be desperate at times like those, when they're like leaving in tents and.
Right. Yeah,
So-
those would be the natural ones to start.
I think he should certainly, it's very interesting, obviously very novel, and is pushing a different frontier. I mean, I come from the other extreme of the world. It's really, this really affects humanity. This is really engineering grand challenge, which actually affects societal well-being. So we want to congratulate our speaker here.
Thank you so much.
And thank you very much.
Kind invitation. Thank you.